In this video, we are going to talk about the reactions of alkenes. We'll be talking about the stability of alkenes, hydrogenation reaction, and elimination reaction of alkenes. Under the elimination reaction, we'll talk about Zaitsev rule and dehydrogenation reaction. So let's start off with this question. Arrange the following compounds in order of increasing stability and also in order of increasing boiling point. Based on your answer, indicate whether the following statement is valid. The higher the boiling point of a compound, the more stable it is. So the compounds are 1-pentene, 2-methyl, 2-butene, 2-pentene, and 2-methyl, 1-butene. But the first thing we need to do is to draw those compounds. The first one, which is we label as A, is 1-pentene. So this is the structure of 1-pentene. The B, the second one is 2-methyl, 2-butene. So this is 2-butene and it has a methyl group. And then C is 1-pentene. 2-pentene. So this is the structure of 2-pentene. And then the last one is 2-methyl, 1-butene, which is D. So we have a 1-butene and then a methyl group on carbon number 2. So these are the structures of the various compounds. Alkyl substituent around carbon-carbon double bonds tends to stabilize those carbon-carbon double bonds by donating electrons into the carbon-carbon double bond through inductive effect. And therefore, let's talk about the di-substituted alkenes, the tri-substituted alkenes, and then the tetra-substituted alkenes. So an example of a mono-substituted alkene is this alkene over here. The alkene has just one alkyl group that is substituted around the carbon-carbon double bond. So we are using R to represent an alkyl group. And then a di-substituted alkene is an alkene that has more than one alkyl substituent around the carbon-carbon double bond. So let's assume this is R and then R1. And then the tri-substitute, this is a mono-substituted, this is a di-substituted. Let's come to a tri-substituted, which is carbon, 3 alkyl groups around the carbon-carbon double bond. And then the last one is the tetra-substituted. That means that all the carbon-carbon double bonds have been substituted by alkyl groups. The most substituted carbon-carbon double bonds is the most stable carbon-carbon double bond, and therefore the stability increases in order from mono-substituted alkyl group to the di-substituted alkyl group to the tri and then the tetra-substituted alkyl group. This is why a non-terminal alkene is more stable than a terminal alkene. Let's determine the kind of substitution around the compound that we're given in the question. So the A, you can see that this is one alkyl group around the carbon-carbon double bond, and therefore A is a mono-substituted alkene. And then for the B, you can see that 1, 2, 3 alkyl groups around the carbon-carbon double bond, so it's a tri. And here is 1, 2. 1, 2, 2 is a di. And this one is 1, 2. So this one, 2 is also a di. And what we said was that in terms of stability, the di is greater than the mono, and then the tri is greater than the di, and then tetra is greater than the tri. But in this case, we don't have a tetra substitution, and therefore the most stable compound will be the tri-substituted alkene, and therefore B is the most stable. And then the least stable is the mono. So A is the least stable, and then B is the most stable. Let's come to C and D. You can see that in C is a di, and then D is a di. However, C is a non-terminal alkene, and then D is a terminal alkene. And we established that non-terminal alkenes are more stable than terminal alkenes, and therefore C is more stable than D. So in terms of stability, A is less stable compared to D, and then D is less stable compared to C, and then C is also less stable than B. So the most stable is B, then the least stable is A, and then D is also less stable than C. So in terms of increasing stability, then it starts from A to D to C and then to B. The second part of the question says that we should also determine the increasing boiling point. The most stable compounds are those with the higher boiling points, and therefore this is also in order of increasing boiling point, and it's also in order of increasing stability. Then the last part of the question says that based on your answer, indicate whether the following statement is valid. The higher the boiling point of a compound, the more stable it is. Now, this statement is not a valid statement. It is a false statement. It is a false statement because let's consider cis-butene and then trans-2-butene. Let's consider these two molecules, cis-2-butene and then trans-2-butene. Cis-2-butene is more stable than, trans-2-butene is more stable than a cis-2-butene. However, if you come to a trans-2-butene, the alkyl substituents around the carbon-carbon double bonds tend to push electrons into this carbon-carbon double bonds in opposite directions, and therefore the dipole moments around this carbon-carbon double bonds cancel out. Because the dipole moment cancel out, trans-2-butene behaves like it becomes a non-polar molecule, and then non-polar molecules are held by the weak van der Waals forces, and therefore trans-butene has a low boiling point. However, for the cis-2-butene, the alkyl substituent push electrons into the carbon-carbon double bond in the same direction, and therefore this cis molecule has a net dipole, and because of the net dipole, cis-2-butene is polar, and because it's polar, it is held by stronger forces compared to the trans-butene. So though trans-butene is more stable than cis-butene, cis-butene has a higher boiling point than the trans-butene, and that is contrary to the statement that the higher the boiling point of a compound, the more stable it is. Consider this alkene. If you put in hydrogen gas in platinum, this molecule will go to the alkene, so it will become RCH2, CH2, and then R. So this is called the hydrogenation of alkenes, and it is an addition reaction. Now let's talk about elimination reaction of alkenes. The first one we will talk about is the dehydration reaction. So let's talk about dehydration reaction. Let's consider ethanol. So this is the structure of ethanol. If you put in concentrated sulfuric acid and you heat this whole solution, you are going to dehydrate, remove water from it, and therefore this will become an alkene. The other reagents that can be used in place of sulfuric acid is potassium hydrogen sulfate and also phosphoric acid. These are all strong acids that can be used for a dehydration reaction, but they must be concentrated. What if we were given a propanol, 2-propanol? Now consider this molecule. If we put in potassium hydrogen sulfate in heat, what will be the product we get. We see that in this case, we also get one product. It is going to remove this water molecule from it. And therefore, we are going to get a CH3. Sorry, there is a proton here. So this is the product you are going to get. What if instead of 2-propanol, it was 2-butanol? Let's consider 2-butanol. What if we put in phosphoric acid, concentrated phosphoric acid in heat? What will be the product formed? You will see that there are two products that can be formed. It's either this water molecule is removed or this water molecule is removed. So there are two products, which is we are going to get. So these are the two products that we will get. And this will lead us into the Zaitsev rule. Which of these two products is the major product? According to the Zaitsev rule, the major product is the more substituted product. And if you come here, you will see that here there are two alkyl substitutions, but here there's only one alkyl substitution. So this is a monoalkene, and then this is a dialkene. So the major product is going to be the dialkene according to Zaitsev rule, and then the minor product is going to be the monosubstituted alkene. That is the minor product. Now write the product for this reaction, which is this molecule in concentrated sulfuric acid under heat. So you see that we need to use the Zaitsev rule here. There are two products that can be formed. The first one is this product. We can cleave this proton and then this OH molecule to form an alkene here. Or the other product that can be formed is this proton and this OH. So there can also be another alkene formed here. Now, which of these two will be the major product? According to Zaitsev rule, the major product is the product that comes from the more substituted. And because the major product has to come from the more substituted alkene, then this becomes the major product. And then this becomes the minor product. Consider this reaction. What will be the major product formed when this molecule is put in concentrated potassium hydrogen sulfate in heat? The product will be, you see that there is a proton here, and there is also another proton here. So there are two major products. There are two products that can be formed. We can form this alkene over here, or we can form this one over here, which is this alkene. However, this will be the major product, and then this will be the minor product, because this is the more substituted alkene. How many products will this reaction form? This molecule in concentrated phosphoric acid, what will be the product? You see that this reaction will only form one product. And it will form one product because with reference to this carbon, there is no proton to go together with the OH to form water. This is the only place where there is a proton, and therefore it will form only one product. So this is the product that we are going to form. Let's talk about dehydrohalogenation reaction. So let's assume we have a haloalkene. If you remove hydrogen plus an alkene from a haloalkene, you will form a corresponding alkene. And this reaction occurs in potassium hydroxide in ethanol that has been diluted in ethanol under heat. We are going to get an alkene. So let me show the protons on this alkene. So this will be the product. So consider this reaction. What will be the product in a dehydrohalogenation reaction? So consider this reaction. What will be the product formed in a dehydrohalogenation reaction? You see that there is a proton here and there is another proton here. HCl could be removed from here and HCl could also be removed from here. And therefore this reaction will form two products. We will have this product and then we will also have this product in the reaction. However, this will be the major product because this product is coming from the more substituted alkene. Because you can see that this is a tri-substituted alkene and this is a di-substituted alkene. Therefore, this becomes the minor product. So what will be the product formed in this reaction? You can see that this is a dehydrohalogenation reaction. So we can remove, let me show this proton here and let me show this one here. So you see that we can remove this to form an alkene over here, or we can also remove one proton from here and this proton to form an alkene here, and therefore this reaction will form two molecules. So one of them is, and then the other is this molecule. So these are the two molecules you are going to form in the reaction. Considering these two molecules, this will be the major product and this will be the minor product. This will be the major product because this is coming from, this alkene is the most substituted alkene because this is a tri-substituted alkene and this is a di-substituted alkene, and therefore this becomes a minor product and this is a major product. Let's talk about the elimination reactions of alkenes. So you can also form alkenes from alkynes. If you have an alkyne and you put in hydrogen gas and platinum, you can form a corresponding alkene. However, this reaction will not give you an alkene, but rather an alkane. So this reaction will give you this molecule over here. So to prevent this reaction from going to the alkane product, what you need to do is to put in a catalytic poison. And the catalytic poison you can put in is sulfur. You can put in sulfur or quinoline. If you put in sulfur or quinoline, then this reaction will not go to the alkane product, but rather it will come to the alkene. So this is the product you are going to get when you put in a catalytic poison. However, if you do a hydrogenation reaction, you could form a cis alkene or a trans alkene. In order to form a cis alkene from an alkyne, in the hydrogenation reaction, you use Lindless catalyst. If you use Lindless catalyst, then you will form a cis alkene. However, in order to form a trans alkene, you need to use sodium in liquid ammonia. And you can form a trans alkene.